So today's Sharcnet General Interest webinar is titled All About Job Wait Times in the Graham Queue. Now, this content really relates pretty much directly to the other general purpose national system, Cedar. They both share the same schedulers and they have a very similar format in terms of the node structures. So a lot of what I'll be talking about today is really applicable to the current general purpose systems at Compute Canada. And another thing that we're updating is that this is also in the context of a new national system that's allowing for a certain specialization of jobs to happen, and that's the new exciting Niagara system in Toronto. My name is James Desjardins. I'm one of the HPC consultants with Sharcnet. My home institution is Brock University. So we choose these lunch seminars largely, a lot of the time is based on the sort of tickets we get, and we try and cover topics that we think would be most valuable to researchers' throughput based on the questions that they have coming through our ticket system. A common issue, and this is really, this applies to all researchers who are using these national systems, particularly while we get these new systems online and optimized to be serving the national workload that we have with our researchers. Now, the common questions that are coming up that I really want to try and help researchers address today are very important ones that everybody has to deal with. So the question, why does a job take a long time to start? This is a very important question. I think anybody who's doing substantial research on these systems, and this is really why you're moving to these large compute clusters, is that we realize that the wait time that a job has in the queue can be a non-trivial part of the time to result that researchers are getting. So we spend a lot of time helping researchers optimize their code, and researchers are investing a lot in developing these strategies. And then you get them optimized, and you go into the queue, and then they might end up waiting a long time in the queue. It's very important to recognize that the wait time in the queue on these large and heavily allocated systems is an important part of your timeline in the research. Now, what we want to do today is really describe the variables that you need to interpret and sort of understand what those wait times are. Now, the next obvious question is there anything that can be done to make a job start more quickly? So this is a key issue. What we talk about are three main overarching themes that determine the wait time of a job. Some of them the researchers have no control over, but there are aspects of job submission that the researcher can make decisions about and influence the wait time in the queue. So in the conclusions, this is really what we're going to get to. Is this question, we can understand the wait times, but are there any situations where there's something that a researcher can do about it to improve wait times? And then another issue that comes up quite a bit is, why does a job start time estimate keep moving into the future? This is a very important aspect of this whole thing. We can give you all the tools to understand how the cluster is working in terms of scheduling jobs to run, getting them to execute, and knowing what the wait time is. But it's very important to also recognize that this is an art form. A concrete prediction of a start time for many use cases is not possible. The start time can keep changing constantly, even whenever the scheduler itself thinks that it knows when the job is going to start. So this is another thing we'll go over, defining these sort of confusing aspects of whenever a researcher is investing effort into understanding what queue wait time might be. We want to make sure that the appropriate grain of salt is taken with that, because the wait times are constantly being recalculated. So I mentioned that we're going to break things down into basically three general factors that we want to consider whenever we're trying to understand the wait time, and ideally, try and get a good prediction of wait time, if not even better, to actually reduce the wait time. So the things that we need to understand are some scheduling basics. So scheduling is based on the resources in a node, and a job is basically a request for resources. The shape of the job, or the footprint of the job, is basically the amount of resources. So it's a multi-dimensional rectangle that has to fit into the resources on a node among all the other jobs that are currently running and are requested to run. Now, this is a very difficult job for the scheduler, particularly in the context of a heterogeneous cluster like both Graham and Cedar are, and with a massively variable workload. Researchers are submitting all kinds of different shaped jobs, and the different footprints that those have in terms of the resources that they're requesting have to fit together as tightly as possible in order for the scheduler to obtain the maximum utilization, so basically how much work the whole cluster is doing. So understanding the way that the node is structured, what those resources are, and then what a job looks like in that context. So the first thing that we're going to do is go over visualizing what it looks like. So basically what a node looks like in terms of its resources, and then what a job looks like in terms of its footprint on those resources and how it's trying to fit together with the other jobs. Now, the next thing, so clearly the footprint of a job will affect how easily it can fit into a system. And the difficulty in fitting a job into the system often has a big determination on its wait time. The next thing that has a very large determination on the wait time, it has to do with some job queue basics. So these are factors that affect the order of jobs in the queue, or the priority of work. This is one of the main factors that determines the wait time of a job. And there are several things that affect the priority of a job. And that's really how jobs get ordered once they're submitted. So there might be thousands and thousands of jobs in the queue, and they aren't just handled at first in, first out. The job queue is constantly resorted based on a bunch of factors, and understanding these factors really help determine, how far down the line your work is that you've submitted to the queue. Now, the final thing is the actual cluster resource basics. So the cluster has resources, and the resources are the nodes. So we talk about what it looks like inside of a node in terms of the resources that are available to perform the compute and what a job looks like on that node. But also the accumulation of those nodes is the cluster. Now, we have a whole bunch of nodes, and those nodes are organized, or they're segmented so that certain jobs are more likely to execute in certain parts of the system. So even though there's a bunch of nodes that have identical hardware inside, there are partitions that determine certain job shapes that will favor to run on some of them, and in some cases are not allowed to run at all on others. So understanding these partitions is important in terms of understanding how many resources your work has a chance of running on. And by increasing the number of resources that your job can run on, you can also increase your chance at having a job run more quickly. So that's why this third parameter really has to be explored. So let's just get right into visualizing the first factor, this scheduling basics and node resources and resource requests. So a resource request is a job submission. You say, I want something to run. The scheduler doesn't really care what is going to run. All that it cares about is the resources that you're requesting. So there's the amount of time, there's the number of cores, there's the amount of memory, and then there's different shapes that can take. So this group of squares is a representation of a single node. Now, a node is built up of resources. So in this case, we have cores, we have memory, there's other things. We have some specialized hardware in some nodes, for example, GPUs. We might have large memory nodes. And that's really what makes up the heterogeneous system. And then we have things like software licenses that are resources. And then, of course, we have this over a period of time. So in this visualization, across the bottom, these are cores. So this demonstration is showing a node that has 10 cores. And then this bar on the side represents the amount of memory that is available to those cores on this node. In this case, we're going to say that it has 10 gigs of memory. And this red part on the side is basically just saying there's some overhead on that memory that's just dealing with the system, the OS and things like that. Now, the axis going up this way is time. So basically we have the right now, and then this is the future in time as we move up the y-axis. And this is basically the visualization of what a node looks like over time in terms of the resources that I'll be talking about, which is mostly the number of cores, the amount of memory, and the amount of time that a job is requesting. That basically three-dimensional rectangle is the footprint of a job. What a scheduler does is it's basically accepting jobs via the sbatch function from users who log into the system. And pretty much all production work on these national general purpose systems is done through the scheduler. Now, the scheduler receives these requests for resources, and then it goes through a scheduling cycle. So in this case, this line represents the current scheduling cycle. It is about to dispatch a bunch of jobs to the system. And then that scheduling cycle just moves forward in time. So after a certain interval, it's now at the next scheduling cycle. It tries to dispatch whatever jobs it can dispatch at that time. So we have the node characteristics in terms of the cores and the memory over time. Now what we want to start looking at is what a resource request looks like. What does a job look like? So in this case, we see that we have a list of job sizes, or the footprint of a bunch of jobs. And this list is basically the current queue that the scheduler is having to deal with. So at this current time in this scheduling cycle, where this blue line is, it sees the, what is this? There's 5 jobs in the queue. The job at the top of the queue is going to run for 1 hour, and it's requesting 1 gig of memory, and it's defaulting to 1 core. So this job at this scheduling cycle can fit into the current interval. It takes up 1 core for 1 hour, and then it takes up 1 gig of memory. That's the footprint of that job. Now, a larger job is requesting 6 hours and 8 gigs of memory, and is a threaded job that's looking for 8 cores. So we see the footprint of this job is substantially larger. Now, of course, the larger the footprint, given fixed resources on any node, a larger job is harder to fit. But still, this assumption that this is basically a brand new system that just got turned on and there's nothing currently running, the scheduler can fit this in here right away, because there's both enough cores available to run, and there's enough memory to fit that in. Now, the next job in the queue is requesting 1 hour and 10 tasks, and just a little bit of memory per CPU. Now, this job can't start at this last time interval, even though there is 1 core available on this system. This is an idle core. At the previous scheduling cycle, there's no memory left. All the memory is taken up by the other 2 jobs and the overhead. So it has to wait for the next scheduling cycle. This job having to wait for the next scheduling cycle is a wait time in the queue. This job did not start immediately. It actually had to wait for the completion of this other job. Okay. Now, what the scheduler is dealing with is actually a huge accumulation of jobs in the queue, trying to fit as many of the current jobs in at each scheduling cycle as possible. So this job had to wait until the completion of that 1 hour job, but because it's a MPI job, it's asking for 10 tasks, it was actually able to start on 2 cores on this node, and then this represents it was also able to dispatch the other tasks of this job on other nodes. So being able to distribute this MPI job across nodes helped it start now. Whereas if this would have asked for all 10 of these tasks to happen on the same node, it wouldn't have been able to start until after the threaded job completed. So this is one of the properties that we'll talk about later. In terms of MPI jobs, either trying to pack them onto a node where performance can be substantially better, particularly if it's a full node job, versus allowing it to be distributed across nodes. This is one of the aspects that we are really trying to facilitate in terms of designing the scheduler algorithms. Now, the next job is looking to run for 2 hours, and it's requesting 9 gigs of memory. So even though this is only running on one core for 2 hours, and this whole period since the completion of that MPI job, on this node there are 2 cores available, this job is not able to fit because it's requesting so much memory. So because of the memory request, this job will have wait time that is another, so it didn't start right away, and it basically doesn't start for something like 6 hours. So that wait time is due to the memory request, as this node, even though it has enough cores available, is saturated for its memory beyond what can be satisfied for this job. And then the next job is 1 hour, and this one specifically is requesting to run on one node where the number of tasks per node is 10. Even though it's asking for a relatively small amount of memory per core. The issue with this job, as it's quite similar to the job that we saw above here, and that it has the same number of tasks and the same amount of memory, is that this one has requested to happen in a full node. This job has to wait until after everything is complete because it needs the entire node to be free. There can't be anything running on the node at the time that that job runs. Now, all variations of job shapes basically come into the representation on this slide. You have a serial job, a certain amount of memory. You have a threaded job with a certain amount of memory. You have an MPI job that can be distributed across nodes. You have a serial job with a massive amount of memory. And then you have an MPI job that's packed onto a single node, or a bi-node job. And these shapes are what really have a lot to do with determining the wait time that a job will see in the queue. Now, the next thing that happens is we're going to be talking about how the priority is sorted. Another thing that the job footprint determines is how the account that submitted the job is going to be billed for the execution of that reservation. So a job is a reservation of resources. Regardless of what it actually uses in terms of memory and the number of cores, what the scheduler reserves for that job is what gets billed. Now, this has a property that isn't always explicit right off the bat. Now, let's look at what these jobs actually get billed. Now, we talk about billing in terms of cores, and we talk about targets in terms of cores. So if you're doing a resource allocation application, you talk about, I need to basically have this many cores running over the year of my allocation, or sometimes call it core years, which can be misinterpreted as always ending up with that much actual cores for that duration. But what it actually is a target. So the target is that if you always have jobs in the queue that can be working, the scheduler will adjust your priorities so this many cores can always be running throughout the year. Now, whenever you run a single core job with 1 gig of memory, you're basically charged 1 core. So for that hour, you were charged 1 core. For the 8-core job that was requesting 8 gigs, it was charged 8 cores. This is pretty intuitive. The parallel MPI job across nodes was running 10 tasks, 1 task per core. It was charged 10 cores. It also had a very small amount of memory requests. Now, the next job that we see is a serial job. It's only actually performing operations on a single core, but it is requesting all of the memory that's available in the node. This job is charged 9 cores worth. It's basically the equivalent percentage of the memory of the system is charged by core. Now, in this example, we're basically saying that 1 core is equivalent to 1 gig of memory, but that's slightly different on the actual Graham and Cedar clusters, where the charge is 4 gigs is equivalent to 1 core, because that's basically the percentage that's made up. Now, even though this one is not using up all of the memory of the system, it is using up all of the cores. So this one is using 10 cores, is being charged 10 cores. So what it ends up being is a job is charged either the number of cores that it's using, or it's being charged the core equivalent in memory, or whichever one is larger. That's basically the charge. So what we end up having is the core equivalent charging is the larger of either the number of cores that was used or the percentage of memory on the node in terms of cores, the larger of the two. So this all has to be interpreted in the actual anatomy of Graham as a heterogeneous node shape and billing system, very similar to what's at Cedar, but then different from what's at Niagara. Now, the legacy systems at Sharcnet, what we always had was basically a variety of systems, and part of what the researcher would do would be decide which system to use based on that system specialization. For example, we had GPU clusters, we had large core count serial farming clusters, and then we had a smaller cluster that had large amounts of memory per node. Now, what would happen is, based on the researcher's footprint, the type of work that they were doing, they would decide which system to use. That was part of the process. Now, what we're doing with the national systems is we're building these massive general purpose systems that contain nodes of all of these different varieties. So Graham, for example, has, a majority of cores have 32, or a majority of nodes have 32 cores per node, and you can run all types of jobs on those. Of these 32 core nodes, some of them have 120 gigs of memory, some of them have 256 gigs of memory, and some of them have 512 gigs of memory. There are also different types of nodes. So we have very large memory nodes that have 3 terabytes of memory, and there are only 3 of these, and those have 64 cores per node. Another thing that we have are actual GPU nodes right inside the system. Now, regardless of where a job ends up, the billing of the core year equivalent is always, if you use 4 gigs, that's the same as using 1 core. So a serial job at 8 gigs is charged for 2 cores in billing. Now, the thing that I want to get across in this is that part of the process in the legacy systems, when we were working at Sharcnet across the various different systems, was that part of the researcher's process was actually deciding through our documentation and through support which system to use, and then that's where you ended up submitting jobs to the scheduler. Now, what happens is the scheduler is taking over that aspect of the researcher's role in making the decision. And what we're going to go over is how the scheduler is making those decisions about basically, if you put all those systems in, if you put all those different types of nodes into one system, how is the scheduler now making that decision about what you were choosing before? Now, in a very exciting way, we're also now that the Niagara system is online, we're now able to start doing that isolation again, where these very large parallel systems, beyond 1040 cores, are being encouraged to go over to the large parallel system in Niagara. So what we're able to do now is, one of these types of jobs that requires special resources, but also has a very difficult footprint to schedule in a general purpose system, can now be offloaded into Niagara. And Niagara doesn't have to deal with all of these other, various footprint jobs. It just has to deal with the large memory. So we're starting to get back into this balance. So now that we know about how the footprint of a job interacts with the actual nodes, we want to get into the job queue basics. So this is the factors that affect the order of jobs in the queue, or their priority. Now this is a major factor to how the whole thing works. And this is where I think the actual duration in the core isn't as meaningful as a lot of us think, based that the other factors that affect the priority or the sorting of the queue are more important. So in this case, we have to understand the fair share. So the scheduler is always trying to dispatch as many jobs as possible, as tightly packed into the systems as possible. So it's always trying to increase the usage of the system, trying to get the most work done all the time. And it's also trying to, and by doing that, it can minimize the wait times of the jobs. But it's also trying to do that in a fair way. So what there ends up being is a share target. So each account, each user, and basically a user group, has a usage share target. And we're going to look at this directly in terms of cores for now. Now, when an account usage, so basically the resources that have been reserved for work by that account, is above the target, the priority of that account goes down. Now, the priority of that account is inherited by every job that account submits. Now, when an account usage, and that is again the resources that are reserved, independent of what actually is used in the job, is below the target, the priority goes down. Sorry, it goes up. So let's just visualize what that looks like. So let's assume that we have 10 accounts. In the simplest form, we have a node that has 10 cores, and there's only 10 users. And these users are all equal. We want them to get the exact same usage over time, regardless of how many jobs each of them are submitting in what form. Okay? So let's say right now, a brand new system just started up. It's got one node, and it's got 10 cores in that node. It has 10 users, and all these users are being treated equally by the scheduler. Each of these accounts has a target share of one core. So if they all submit one job right now, they're all equally as likely to run, and those jobs will all start right now. So at this scheduling cycle, the first scheduling cycle, all 10 accounts that have an equal target share of one core all start one job. And then here we see basically in this first scheduling cycle, we have accounts 1 through 10, and this is basically a representation of their priority. And what we have here is basically first in, first out, FIFO. Now, on the next scheduling cycle, let's say that account 1 submitted 2 jobs, account 2 submitted 2 jobs, and then accounts 5 through 10 each submitted 1. All of those jobs are just as likely to start, because at the time of the first scheduling cycle, all of the jobs stayed on their target. So they're all still equally likely to start a new job. If account 1 happened to submit more jobs and account 2 happened to submit more jobs, then 3, then accounts 3 or 4, then those jobs are allowed to start now. So account 1 and account 2 were able to burst beyond their target share of the system because the resources were available and they had jobs in the queue. Now, what happens for the third scheduling cycle is now if every account now submits one job for one core, so we have 10 accounts, each account having a share target of 1 core, they all submit jobs, even if they submit it in the order where it goes from account 1 to account 10, the order in the queue is no longer first in and first out. So basically, if at this time account 1 through 10 submitted a job for 1 core in serial, the scheduler would not see it in that order. The scheduler would reorder the queue such that account 3 and 4 that fell below their target during the second cycle because they didn't have jobs running, so they are now below their target share, their priority has gone up 0.75. Accounts 5 through 10 are still on their target. They've run 1 core the whole time. But accounts 1 and 2 are the last ones to be considered. So if there are any constraints on the system during that time where some nodes were not available, it would have been accounts 1 and 2 that would not have run on the system, even though they may have been the first ones to submit. This is a really important aspect to understand, in that it isn't the actual time, the duration of the time, that has the strongest role in terms of how the scheduler sees the ordering of the jobs that it's considering for dispatch onto the system. Whenever the scheduling cycle happens, the scheduler starts from the top of this priority list and works down, fitting the jobs that it can onto the system. So even if, for example, accounts 3 and 4 would have submitted 2 jobs at this time, and accounts 1 and 2 would have submitted 1 job each, accounts 1 and 2 wouldn't have run on this scheduling cycle because they're being, brought back onto their target. Now, targets are not that simple. In production, target shares are not equal. There are resource allocations. For example, there are resources for research groups, and the research portals and platforms have allocations, are defined by a unique share target. The rapid access service accounts, or the default accounts, is the equal shared residual system resources available beyond the allocations. Now, the rapid access service target is the number of residual cores. So once all the allocations, shared targets, are on the system, the number of cores left over divided by the total number of default accounts is basically the target share on the system. If you don't have an allocation, this is what's determining your priority in the system. This is what's manipulating basically where your work ends up in the queue sorting based on your usage. Now, if we look at that, we had looked at the previous accounts as being, account 1 through 10, each one having 1 core. But really what it looks like is we'll have a resource for research groups, a first award here, and then a second larger award, a third award, a fourth award, and then what's left over are these 2 cores on the system. Those 2 cores are going to be what's shared equally across all of the default or the rapid access accounts. Now, so far we've just been talking about the node itself, where the jobs actually run. But the next thing that we want to consider is how that node fits inside of the cluster itself. So the cluster is basically just the accumulation of all the nodes that make this up. So we're going to change this visualization from this node that we've been looking at over a certain period of time, and we're just going to drop it down into this box and then show a whole bunch of boxes representing basically a portion of one of the general purpose systems. So for understanding the cluster resources and the segmentation of nodes in the cluster into partitions, I'll just give a bit of a description here. A partition is basically how we restrict jobs of specific shapes to specific node sets. So certain types of footprints are allowed to run in some places, not others. So full node jobs can run on most any node, and this is called the binode partition. So of all these nodes, if you submit a full node job, basically where you're requesting that this job consumes an entire node and is really sort of an optimal way of running, that can run pretty much anywhere. Those are also relatively difficult jobs to schedule because they require that an entire node be completely idle before the resources are available. Now, another thing is that short run times, so jobs 3 hours and shorter, can run on most any node as well. So here, I'm just going to start drawing the partitions. So, we have these specialized nodes over here. So we have different types of memory. We have interactive nodes, large memory nodes, and then GPU nodes. For this demonstration, I'll really just be talking about the sort of the base nodes, or the typical 32-core and 128 gigs of memory nodes. And that's the large pool of nodes on the cluster. So what we know right now is basically if you submit a 3-hour full node job, it can run on any of these nodes. Now, longer runtime jobs have access to fewer nodes. And this is accomplished by partitions. So basically, 12-hour jobs have access to a subset of those nodes. Now, if I submit a 3-hour job, I can end up on this node here, which might also be running 12-hour jobs. There's also a partition for 1-day jobs, for 3-day jobs, for 7-day jobs, and for 28-day jobs. But the longer the job times are, the fewer resources that a system has access to. And this is an important part of understanding what the effect of long run times are on your job wait times. Now, the next thing beyond the amount of time is that partial node jobs, or bi-core jobs, that aren't reserving a full node have access to fewer nodes. So we have a bi-core partition. So if you're requesting jobs that don't take up a full node, those are actually isolated to a certain proportion of the entire cluster. Now, this is an example. You can monitor which core count is actually available to that type of job by something I'll look at later. Now, the last partition is the backfill. Backfill jobs can run on most any system as well. So overall, a backfill job can run on any of these nodes. So let's just take a look at the difference between a binode versus a bi-core. So binode jobs can perform better, and bi-core jobs have more opportunity to run. So basically, a bi-core job is something that can fit into little places. So here we have an example of a binode job that's requesting an entire node of 32 processes, and that's what the blue one looks like. It's taking up this full node. It can run anywhere, and it's just asking for 3 hours. Now, this job isn't specifying that it has to be packed onto a single node. It's still 32 tasks, but it can be distributed all over the place. So it can fit into all kinds of little nooks and crannies, and it can get scheduled relatively easily. If enough of those bi-core jobs distribute themselves across the entire cluster, then no binode jobs can run. because they need entire nodes to be idle. So this is why this partition exists. We want to make sure that by trying to run a full node job, which for many reasons can be more efficient and more predictable, that those jobs have an opportunity to run and that the system doesn't just get filled up with by-core work. Now, backfilling is a very important part of this whole equation. So backfilling means that jobs can start before higher priority jobs if they complete before the higher priority job can begin. So here the P10 is basically the priority of a job. This is a very high priority job. What I've done at this scheduling cycle, I said, well, I'm going to submit my job at a lower priority, but this job can actually start before the higher priority job because it will complete before that job can ever start. So what we have here is a job that is still going to run for another 3 hours, and I'm requesting that my smaller job only run for 3 hours. So I'm telling it that I'm only reserving resources until the next possible chance that a higher priority job can start. Now, this is one of the important properties of having a large heterogeneous system that's under one scheduler, is that if you have nodes that are running these jobs of very large footprints, that will often leave a lot of gaps. Now, you want the scheduler to be able to find little jobs to fill all those gaps in with. Now, at this point in the scheduling cycle, the scheduler might actually give a start time estimate that this P5 job is going to start at the beginning of the next hour, which is great. The problem is that this can change at any time, and it can change for many reasons. For example, this can change because the job that was running, the job that was causing the high priority job to not be able to start for 3 hours, might actually end in 2 hours. If that happens right now, then the start time of the high priority job drops back 1 hour, and now your job can't start for another 3 hours until after that was finished. So even if it was very close to starting and the scheduler had a very good idea that it was probably going to start, that start time can get changed dramatically right away. Another reason that I can change right away is because the priority of accounts has such a large impact on the sorting of the queue, higher priority jobs can come into the queue at any time. So regardless of how long a job has been waiting, very often, if it's in the default account, a higher priority job can come in now, can take a very long time, and this job will get pushed back behind it. On every scheduling cycle, the queue is resorted based on what is in there now, and the priority of an account has a very large impact on that sorting. So, based on all this information, what is it that we can try and access? What is it we can try and understand about the state of the jobs in the queue? Now, it's a very large system. There are many, many jobs in the queue, and what we want to be able to do is, although we don't have any influence on what jobs are in the queue, we can take a look at them. So the account call, the S-Act, is a way where we can look at all jobs in the system since a given time. So this would basically display everything since midnight last night. And we can show what kind of account it was. We can show what partition it ended up in. We can see when it was submitted, when it started, when it ended, what the total elapse of the actual execution was, what time limit was requested, what memory was requested, how many CPUs, how many nodes, and what the state of the job is. Now, by looking at these columns of all of the jobs in the queue, both ones that have completed in the past and ones that are currently waiting, by basically accessing parts of that list, for example, if you're using a default account, only listing the default accounts, and then only listing the jobs in the partitions that you are working in, you can start to form a pretty good estimate of how similar jobs to yours are actually, how long those are waiting. Now, whenever I'm working with a researcher trying to make those job estimates, that's what I spend my time doing, is trying to build an accurate estimate based on the occurrence of similar jobs in the system. Although it's very hard to predict what's going to come into the system in the meantime, we do have a very large amount of data that represents the whole spectrum of types of footprints in there. The other thing that we can do is we can use SQ to show the queue of jobs, the jobs that are currently waiting, in the actual order that the scheduler is considering them to run. So this sorting the SQ command by the priority, and then giving it certain where we get to see what type of account it is, what partition it's in, the number of cores it's requesting, how long it's been in there. We can show all of these properties and also show it based on the actual order that the scheduler has resorted it to go into a running state. Now, a couple other commands. There's the partition stats. The partition stats shows you basically the layout of all the partitions, how many jobs are queued in that partition, how many jobs are running in that partition, and how many are idle. And then the sinfo, this can be used to show the states of all of the nodes in the system. And scontrol show partition shows you the actual definitions of the partition. While I'm talking about the different partitions that exist right now, if you call that on the system, you will actually see the definition properties that are determining which partitions are currently on the system. Now, the role of the national scheduling team is to make sure that these partition configurations are best matching the workload that researchers are putting, the demand on the system. Now, the type of documentation that can be used to make these estimates, all of the commands that I was just talking about are available on the SchedMD site. There's also a quick summary, like a two-page thing of the commands to use. For the specifics of the systems, you can go to Docs, Compute Canada, CA, the wiki page for Graham and Cedar. Those two systems are very similar, but if you want to get a view of the different types of nodes they have, that's there. And of course, now that we have a specialized system for large parallel, you can go to Niagara to see basically when you want to move from the general purpose systems onto the specialty system and what's required to get there. In the documentation for running jobs, there's some documentation for these certain things to consider. For example, if you're running MPI jobs, how to make sure that they end up in a by node versus a by core partition. The scheduling policy is always updated online there. And if there are known issues, right, this is always the concern. If you notice that a job is running a long time, the concern and why this often comes to a ticket system is people want to know, is this because there's an issue on the system? Any known issues that we have that are affecting, that seem to be affecting certain account types or job types unfairly, we will post this on the known issues page until it's resolved. Now, there are other examples of seminars that we've done. I've done a short seminar called Gaming the Scheduler at Sharcnet. And although that demonstration uses a different scheduler, the concepts are the same. It's basically what properties can you use to break a job apart so that its footprint is easier to fit in a system. So, at the end of the day, what can be done about wait times? And these are basically the conclusions. So the job resources are the footprints, the shape of the job on the cluster. What you want to be able to do is, wherever possible, decrease the job's footprint. So we want to minimize still accurate requests. So if you're overestimating the memory or if you're overestimating the amount of time, it doesn't matter how much resources your job actually uses. The wait time is determined by the request. So the request of resources should be accurate, and you should try and get your work to be using up the fewest amount of resources as possible. That's where development of the job comes in. Now, if the job runs for a very long time, an important aspect of that is using checkpointing. So checkpointing basically allows a job to stop halfway through and then restart where it left off. Being able to do this, you can actually, submit dependently queued jobs. Instead of submitting, a 30-day job, you could submit a bunch of 4-day jobs that are dependently queued, each one picking up where the last one left off. This type of scheduling is very healthy, not to mention that a long job, if it dies, more information is lost if you weren't checkpointing along the way. So it's a better way to work anyway. If you're running MPI jobs, consider the difference between a compressed onto a single node job versus a distributed across node job. The load on the system, this has a big impact on the wait times. And users have no control over the load on the system that's imposed by other groups. But there are methods to view the state. And by viewing the state of where the load is, you might be able to favor a different type of job submission to get into more available resources. Now, of course, one way that we can affect the amount of resources on a system is the contributed model. Now, that's where a researcher who has a type of workload that isn't easily serviced by a general purpose system can actually contribute nodes and then affect their own priority on those nodes differently than the rest of the researchers. And then in terms of account targets and fair share, so being efficient about usage, both in terms of the number of jobs that you're running and the footprint of the job that you're running. If you're running larger jobs, then necessarily you're getting charged more for them. That will impact your priority. Another thing is if you're doing a bunch of testing with large memory, consider using the interactive nodes for your testing, where the billing isn't running there and you get to do very quick tests on an actual compute cluster. And of course, applying for a resource allocation target. This is how you define a set target that you have for the year, and your priority will be based on that target rather than a default target. This is the model that we work very hard to try and maintain properly. And this is also where we base the resources that we make available to researchers. So other conclusions, basically scheduling policy is prioritizing account target consumption and total system utilization. Job submission should prioritize the optimal running of the procedure. So we still want your jobs to be running at a high performance, so doing profiling and scaling. And you should also consider the feasibility within the scheduling policy for that job to be able to start. On our end, we're working to configure the cluster and the partitions so they'll be adjusted to best suit the system workload that's defined by the users. So on our end, we're trying to monitor and modify the way that it's set up to best suit the distribution of work that exists on the system. Of course, wait times are a very important part of your time to results, and don't hesitate to open tickets regarding the shape and the queuing property by emailing us at support@computecanada.ca, and we can help you go over the options for your actual run that might minimize your wait times. And that's the end of the presentation.